Thank you so much for your warm welcome. There are 5 most important events in time. The creation, very important event. We cannot understand this world if we don't see the creation. Then the fall of man, then the great flood. And then you see here on the time axis the cross. Jesus Christ came in this world and he went on the cross and he is resurrected. And that's the reason that we go to the heaven. And he will come back, the second coming of Jesus Christ. So you see, the great flood is one of this event on the time axis. Let me give a few questions about Noah's Ark so that we understand this very amazing ship. Which ship was not commissioned by any human being and yet it existed? Which ship owner had only one ship and yet this ship, which did not even have a name, was world famous? In the course of history, all sorts of different ships have been built: ore freighters, tankers, passenger ships, submarines. There is this constant demand for these sorts of vessels, and so they are continually being built. Which ship was built for only single purpose? Which ship was built to be used only once, purely for its maiden voyage? Which ship, with a tonnage in the range of an ocean liner, was not built on the basis of design drawings? Normally, ships are built on land. When they are completed, the ships are launched by sliding them into the water. Which enormous ocean-going ship was never launched in this way? Which ship's freight was so valuable that each one of us still benefits from it today? Which ship was used on an endless body of water much bigger than the Pacific Ocean? Which ship of comparable size and importance was built exclusively by laymen? Which ship set sail without knowing its destination? It's the only ship in history with this special points. What is the description? This ship was commissioned by God. He was the owner of this unique ship. The design plans for this ship were also drawn up by God. God was the helmsman of the ship. That is why it needed neither a compass nor a rudder. This ship was built in Noah's shipyard. He was neither a trained shipwright nor an engineer, but a nomad and cattle breeder. However, when God was looking for someone to do the job, he chose Noah because he was the only one he could trust. The ship sailed under God's invisible flag and was put into service when Noah was 600 years old. The ship made only one voyage, its maiden voyage. The ship's freight was the most valuable any ship could carry, the genetic material for every single person and land-living creature who lived after the flood. If this ship had sunk, then we would not be here today. The fate of each one of us is associated with it. Also, of course, this ship could never have sunk, since the designer, owner, and helmsman was one and the same, God. This ship never had a name. The name used in the Bible, Teba, is not a real name, but a term also used for the basket made of rushes in which Moses was hidden. What is the size of the ark? The necessary tonnage of the ark can be deducted from the prerequisites for transport. The ark had to have enough room for all land-living creatures. It also had to be big enough to take provisions to last for a little more than 1 year. There was a basic principle in the work relationship between God and Noah, which is still relevant for us today. Let's come to the first principle. Noah was told to do what he could. What Noah was not able to do, God did. This is why Genesis 6:22 says, "And Noah did everything just as God commanded him." The main idea for the following considerations: Noah had no idea about how to build a boat, and so God had to provide him all the necessary data. Thus, if God provided the measurements for the ship, then from engineering point of view, they must have been the best. Nowadays, we have the necessary know-how to build ships. Therefore, if we employ this know-how along with the all-important tool, the computer, to this problem, using engineering standards, we should come to the same conclusion as the instructions God gave to Noah. Noah had no idea about how to build a ship, and he could never have imaged how big a ship would have to be to fulfill the given purpose. So God gave him the instructions for the size of the ship. The measurements of the boat were 300 cubits long, 50 cubits wide, and 30 cubits high. That gave the cubic capacity of 37,500 cubic meter, or a tonnage of 13,250. What are the important viewpoints for the construction of the ark? Let me give a few points. First one, enough space for all land-living beings. That's what we read in Genesis 6, verse 18 to 20. "But I will establish my covenant with you, and you will enter the ark, you and your sons and your wife and your sons' wives with you. You are to bring into the ark 2 of all living creatures, male and female, to keep them alive with you. 2 of every kind of bird, of every kind of animal, and every kind of creature that moves along the ground will come to you to keep alive." And the next important point is enough store for 371 days. It's a little bit more than 1 year. In Genesis 6:21 we read, "You are to take every kind of food that is to be eaten and store it away as food for you and them." On this picture, we see what happens during 371 days. 40 days it rains, then the flood was on the highest level, and then it goes down. The Bible describes it very exactly what happens on the different days, so that we can make such a construction, such a diagram as shown here. Now let's come to the most important thing for me on this evening. Number 3, taking measures for construction. First point, simple ship design. The simplest construction is a box. Economical use of material. God is economical in use of Noah's power. And the third point is optimal parameters concerning floating stability. What is the solution of the problem? There are 2 parts of work. The first part is God's part. And that's what we read in Genesis 6. "So make yourself an ark of cypress wood. make rooms in it and coat it with pitch inside and out. This is how you are to build it. The ark is to be 450 feet long, 75 feet wide, 45 feet high. Make a roof for it and finish the ark to within 18 inches of the top. Put a door into the side of the ark and make lower, middle, and upper deck. And now the second point is Noah's part. That's what we read in Genesis 6:22. Noah did everything just as God commanded him. Now I will tell you about my job. What Noah was not able to do at his time, I have done a few thousand years later. What is to do? Finding the optimal parameters for an ark using laws of nature, mathematics, and computers. On this picture, you see two ferries. They are on the Baltic Sea, and they are going from Travemünde in Germany to Trelleborg in Sweden. And the size of these ships is equivalent to that of the ark. Noah's Ark is often used for cartoons and books for children. And what we always see is, in most cases, the ark is illustrated as a very small ship. At home, I have a very old Bible, and from this Bible you see the first page, Genesis 1, in old German letters. And this Bible is my oldest Bible. It is a Lutheran text, printed in 1720. It is also my heaviest Bible. It weighs 11 kilograms. Maybe one of you have a Bible which is heavier than this. It's also my most expensive Bible, several thousand euro. But interesting is, in this Bible, there is a very long command, and also there are pictures. And the pictures are very realistic, also in the ark, for the ark of Noah. There are many pages about Noah's ark, and the man who wrote the comments, I think he was a good engineer. And he has described what happened on the different levels of the ark. There are 3 decks on the ark, and he has written what the best way is to bring the animals in which kind of deck. So he said, on the lower deck, there are the lions, the tigers, the camels, the elephants, and the horses, and so on. You see, there are the heavy animals are on the lowest place, and the idea is that the center of gravity of the loaded ark will be as low as possible. We will see it later if we see the mathematical formulas for this. In the middle deck, he said, there is hay and straw and cheese and butter and fruit and zwieback, tools, and so on. Things which are not too heavy. And in the upper deck, there are the owls, the ducks, the storks, the pheasants, the swallows, and so on. We see animals which are light. So now let's come to the material requirement. You see 3 decks and the roof, so we have 4 times the B, and therefore my formula for material M, it is here written 4 times B and 2 times the H. And multiplied by the length, that is the complete material. And this should be a minimum. The complete volume of the ark is B multiplied by H and multiplied by L. Now we can calculate a few formulas, and I have defined a special quotient, Q. Q is the volume of the ark divided by the material required. And that's a very interesting quotient. You see, we can write this formula in two parts, A1 and A2. A1 depends only on absolute values, and the second part, A2, depends only on related values. That's what we see on the formula here once again. So we come to a formula, A2, and this A2 should be a maximum. About the expression A2, I can say, since the expression for A2 contains only the variable b over h, both b and h having the dimension of length, hence it is dimensionless. A2 may appear to be an arbitrary entity since it has no physical or geometrical significance. However, also, it has been artificially derived. We can mathematically find the conditions under which it is a maximum. Q will be a maximum when A2 is a maximum, and consequently M a minimum. That's what we want to find, a value Q which is very high. If we have a very high value of Q, then we will have a minimum of material. We see there are many possibilities to construct an arc. In the case for the maximum, you see it's an arc with the value b over h, it is 0.5. It is most economical for use of material, but you can see it is a very, very unstable arc. The other one, what you see on the right side, it is very stable, but the value A2 is not so high. So it needs very much material to construct such an arc. But from the viewpoint of material requirement, it would be the best arc if we use b over h for the value 0.5. On this picture, you see all the motions of an arc. Some of the motions, you see, have a restoring forces. Motions, and also we have motions with restoring forces, dipping, or with restoring moments, pitching and rolling. There are back movements with initial behavior. The very important thing for the floating stability is the rolling motion. We use a law of nature for floating bodies. This law is discovered by Archimedes. It's very old, you see. The amount of liquid displaced by a body floating in its weighs as much as the body. Here you see two positions of an arc. On the left picture, you see a normal situation, and on the right side, you see an arc with a tilt angle alpha. And there are two forces which we can see, the force of gravity, that is G, and the force A is a buoyancy force. Both forces are equal. And the point where the gravity is going on is the gravity center, and the other point is A is going to the gravity center of the displaced water. Here you see once again an arc with a tilt angle A alpha. We need for the calculation a few distances and coordinates for the floating stability. You see the meter center above, and you see the center of gravity of the complete ship, and the center of gravity of the displayed water. Z is the force of gravity, and A the buoyancy force, and G multiplied by the distance rho, that is the restoring moment. It's a very important moment which brings the arc in the normal position. When I started to calculate the formulas, I had the idea it needs only a good evening and then I'm ready. But when I started, I saw I have to use all the different positions of the arc. And so I had many formulas for the different positions of an arc. Now let me come to the floating stability. Here you see in triangle, it's not important to see all the equations, but let me come to the solution. This formula, number 6, is a very important equation. It's a central equation for calculating the floating stability of any box-shaped ship. And you see on this formula, there are also only related values. And that means the floating stability depends only on related values. B over h, the ratio of breadth to height. The next one is the ratio of center of gravity to the position of height. And the third one is ratio of draft to height. And the very important point is the ratio of distance of the forces couple A and G to breadth. What are the important things here for the floating stability? We have two cases for an arc. The stable condition is if the meter center is above the gravity center SG. It means that the value rho over B must be greater than 0. And the unstable condition is if the meter center is below the gravity center SG. It means if the value rho over B is less than 0. The measurements for an arc, we can say the volume is a given value for Noah's ark, a given value for the purpose. Now what we have to calculate is the value, the right value, the optimal value, B over H. It must be an optimal ratio for economical use of material and good floating stability for the rolling process. And another important ratio is L over H must be an optimal ratio for stability concerning waves. It means the pitching moving. Number 1, I have done the B over H calculation and will demonstrate it now. L over H remains to be done. Now we come to the solutions of the equations and we see it in the diagrams. On this first picture, you see an arc. It's a box which width is 5 times its height. And you can see it is a very stable condition. It is very good on the water. And that's what the curves shows also. All the values rho over B are positive. So we can say all kinds of arcs are stable. Let me give an idea about the parameter for the curves, H0 over H. It shows us how many % of the arc are into the water. What is the displaced water? If this value is 1.0, what do you think what kind of ship it is? It's a submarine, yes? And if we would have the value 0.01, it is in a polystyrene arc with only 1% is in the water. I have calculated all the values because I want to see the behavior of these parameters. Now let's have a look to a square arc where B over H is 1. We see the gravity center in this way is 0.3. It means the gravity center is 30% of the height of the arc. You see in this case, for angles from 0 to 60 degrees or 45 degrees, it is stable. And on the right side, we see there are parameters when it is unstable. If the gravity center is very high, you see also the consequence in the floating stability curves. So it is more unstable than the other way. Now on this picture you see a flat-shaped box where B over H is 0.5. And you see in this case what we can feel, what it is, all the arcs in this way are unstable. So it's not good to construct an arc in this shape. Now let's come to another very important and interesting value for calculating the floating stability. I have defined a value ES. It is the integrated floating stability. It is a function of the level of the gravity center and depends from the value B over H and also from the value H0 to H. We have to integrate the formulas. I have done it for the angles 0 to 90 degrees. For different parameters, H0 to H, and for different high levels of the gravity center. We find a set of curves for values in a diagram with H0 by H is constant. What we see is on these three curves here, the less YG over H, the better is the stability. And that is the function F1, I have named it here. So we have a problem if we want to construct an arc which a minimum of material, then the stability is not good. But if we use a very stable arc, then we need a maximum of material. What to do? We combine both parameters and optimize both parameters by a computer program and find the optimal value. And that's what I have done. I have combined the function f1 and the function f2 by multiplying. So we find a new curve with the name f3. The maximum of f3 shows the arc with the best ratio b over h. The solution you see here. In this diagram, we find the integrated floating stability multiplied by q as a function of b over h. Here in this picture, you see the relative depth of immersion, 30%. It's a realistic value for the arc. And another important point is yg over h, 0.28, the relative height of center of gravity. Then if we use this special value, I assume that it would be a good value for the arc. Then we find the optimal value, b over h, 1.667. This is the same value as we see in the Bible. Let's see the stability curves of this special b over h. We see all the curves show that rho over h, the curves are all stable. We have stable conditions. So we can say we have a good stability and also economical use of material. You are familiar with the Gilgamesh epic from the Babylonian, and on table number 11, it is written, "The ship that you will build shall have the following dimensions. Its length and breadth shall be equal. Its walls were each 120 cubits high. The 4 edges of its decks were each 120 cubits long. I designed its rooms and assembled them together. I installed 6 intermediate decks. I divided it up into 7 floors." And that's what we see here on this picture from the Gilgamesh Ark. It is a cube, and you see the 7 decks. Now, after you have seen the formulas for floating stability, you can say if it is a good ark on the water or a bad one. And you see, you can say it is a very bad ark. Why that? The gravity center is very high because there are 7 decks. And you see also it is a cube. And so it rolls all the time in the water. Now let me come to the conclusions. Now, several thousand years after the construction of the ark, using laws of nature and high-speed computers, we arrive at the most economical and most stable condition for the ark. We can say the best fit in economy and stability that we found is precisely those dimensions described in the Bible. This clearly refutes the assertion by many theologians that the Babylonian Gilgamesh epic predates the biblical source. Our scientific analysis has shown that although the Gilgamesh Ark is more economical, it is very unstable. In conclusion, these results add one more element to the extensive list of discoveries which confirm the validity of the Bible. It's a very good conclusion, and I have found it by using mathematical formulas, laws of nature, and computers. And we can do it nowadays, and so we can see that God gave the best measurements to Noah to construct an ark. So we can say Noah never could know the ratios which we have found now. It is only possible that a God which has all intelligence gave the right measures to Noah, and we can calculate it in the 21st century, and we can see the Bible gives us the right answer. The Bible, we can say, is the book of truth. That is what Jesus said and prayed to the Father, "Your word is true." And that's what it's very amazing if we can see it, if we can do it, and we can come from another way and to tell it that what Jesus said in all cases is true, also by a mathematical way. Thank you for your attention for this lecture.